So on this video we are going to analyze the force and the torque on loops like this one that you are watching on the screen, and well, this is the idea. We are going to study the force first and later the torque for a loop like this one, with three different positions. The first position is this one, position A. So in position A, we see the current. The current of the loop is I, this one. We see the magnetic field is going up. So the force will be always IL cross V. So if you just know what is I cross V, IL is a vector in this direction, okay? Cross V will be this vector, okay? On this one, on this side, there is a force also, and the force is again IL cross B. B is going in this direction, L is going now in this direction, you see L, and L cross B will go in this direction. As a result, we have two forces that is a pair force, and the force will make a torque. So we'll study later the torque, tau. So let's go to find the force on this position for the loop. There is a quantity that is called the magnetic dipole. We call with this letter mu, and the magnetic dipole is the intensity by the area of the loop, by a vector U sub n that is perpendicular to the area of the loop. So you see mu, here is mu. You see mu, why mu is here? Because the area is like this, and a vector that is perpendicular to mu is going like this. Why mu is going in this direction and is not going in this direction? Well, because the current is going like this. It's going counterclockwise on the figure A. So if it's going counterclockwise, mu is going in this direction. For example, here, the current should be like this, is going counterclockwise, and mu is going up, perpendicular to the surface. On here, on this third picture, here, the current is going in this direction. I suppose, yes, it's going in this direction. So mu, you see, perpendicular to this surface of the loop, perpendicular to the surface of the loop, and the magnitude of mu is intensity by area. This parameter is very important to analyze this thing. And what it happened with the forces, that the forces, they make a torque. And what happened with the torque, that this mu is going to rotate and is going to be parallel to B. This is what the force is doing, to rotate the loop in a way that mu is going to be parallel to B. Okay? So let's go to study the forces here. You don't know from me to tell you so much, because it's very easy to see that the force here is here, the force is here, like this, the force is here, and the force is here. There is any torque here? No, there is no torque. There is no way that these four forces will rotate the loop. The torque here is zero at this position. Why? Because the torque, remember, is R cross F. So R is going in this direction and is parallel to F. So R cross F is zero. For this force, R cross F is zero. So the torque here is zero. So what the book try to make you to to see is the following thing. First, there is a force, and here there is a cross product involved. Second, there is a torque, and another cross product is involved, R cross F. Which F? This F. So there are two torques involved. And what he wants you to calculate is that the torque at the end is mu cross B. This is what we want to calculate, that the torque is always mu cross B, and this is a fundamental equation that you will use a lot. So to find that the torque is mu cross B, we have this picture, this one, and the way to calculate is, well, calculating. We calculate the force, and once that we have the force, we calculate the torque, that is R cross F. So if we do it, let's go to do it. This force, let's say, this force F1, okay? F2 will have the same torque. So the torque is the force by the distance that is perpendicular to the force. The distance that is perpendicular to the force is this distance. You see it? You see this distance. But this distance, this is the length of the B. This is the length, so this is B over 2. Cosine of theta will be this, B over 2 by sine of phi. So L is this distance, the cable distance, L. Well, L is what he called, this is V, and this is A. L is A, so we put A. So we calculate the torque. I calculate the torque of the force F1. The force F1 will be, the torque will be the force by this distance, that is V over 2, sine of phi. Okay? But the force, the magnitude of the force, let's go to see the magnitude of the force. The magnitude of the force is I, L, B by B over 2 sine of phi. So will be, for the force 1, for the force 2 will be exactly the same expression, and for the sum I will have the total torque, I will have 2 times this torque. 2 times this torque will be I, L, B, B sine of phi. So you can put this expression like this. L is the distance, this distance. So I, A, this distance, V, this distance, this other distance of the loop, B, sine of phi. What is this? Magnitude of mu. What is this? B sine of phi. So you can write this in a very compressed way, like this one. Tau is mu cross B. So I have calculated the torque of this loop when it's submerged in a magnetic field and when the current is passing through the loop. Let's go to use this equation, okay? Let's go to use this equation, and you make this problem. So this one could be, we have a magnetic field B, let's say 5 Tesla, okay? We have mu like this, mu. So the loop is like this. You see the loop? I don't know how to picture, but this is mu. So let's say that mu is intensity by area. Mu is the vector that is, the magnitude of mu is intensity by area. So I'm giving you the area. When I give you mu, I give you the current and I give you the area. So mu, let's say that is, let's go to put it like this, let's go to put it 3i plus 4k, or 3j plus 4k, and b is 5k. So this is the vector. Mu is 3j plus 4k, 1, 2, 3. This is j, this is a y, j, 3j, 4k, 1, 2, 3, 4k. So the vector mu is this one, is on the plane yc, and the vector b, I said 5 Tesla on the k direction, so the vector b is this one, b and mu. And I want to calculate the torque. Can you calculate? Do it. Very, very easy. I have done. So this torque, what it will do? It will make the mu to rotate in following B, trying to be parallel to B. It will remain like this, mu? No, it will not remain like this. It will oscillate around B like this. Mu will go like this. But the tendency is always that this mu, intensity by area, okay, intensity by area, this is the loop, mu will go parallel to B. This is the tendency. So good luck, good luck.